Hi, in today's video, I'll be going through the uses of binomial theorem in the study of combinatorics. The binomial theorem is a very strong and powerful algebraic identity that you can prove using mathematical induction in your algebra course. But for today, I'll let you see how the binomial theorem, with its abilities and uses in algebra, allows us to simplify our combinatorics identities to make it easier for us. So, let's start with what is the binomial theorem. The binomial theorem expands this expression over here. It says that if x plus y to the power of n, it will equal to n choose 0 xn plus n choose 1 xn minus 1 y plus all the way to n choose n y to the power n. And this is the simplified form, and this n choose r is known as the binomial coefficient. Let's see why that is true, not from induction, even though that will be the most natural way to do it, but let's do it from a combinatorics argument. So, x plus y to the power n equals to x plus y times x plus y all the way to the last term, and there's n times of this. And so, for each factor, you can ask the question whether x or y is chosen. And so, out of these n factors, r of them will contribute to the y, and the remaining n minus r of them will contribute to the x. And hence, the coefficient for x to the power n minus r, y to the power r will just be n choose r, which is also equivalent to n choose n minus r, because remember when we go through in our previous videos, choosing r terms is the same as choosing n minus r terms not to be the same as the r terms. Hence, this will be the coefficient for the binomial expansion, and so we call this the binomial coefficient. So, you can see how easy it is to prove the binomial theorem from a combinatorics argument, and this is valid due to the well-definedness of cardinalities. Now, let's see some applications of binomial theorem. Well, one application is that it helps approximate expressions. So this can be used maybe when you are programming or trying to solve a question without a calculator. And so you have 2.01 to the power of 5, and the question asks you to do it to 3 dp. Then you expand out, you make it 2 plus 0.01 to the power of 5. You can use your binomial theorem to expand into this formulation. And then you can write out 3 terms only needed. Because once 0.01 is to the power of 3, it will add on to the 4th dp already. And so it's not needed. And so this cuts your computational time by 3 other terms. Then you just add them up, and then so you get this to be 3 dp. So this is just a simple example of approximation. Of course, with the use of a computer, you can then approximate it. You can then apply the formula to larger values for easier approximation. Well, while this is the applied use of binomial expansion, we want to use it in math to help us simplify algebraic expressions. So it can help us in proving certain identities, which we can also use combinatorics, but the binomial theorem, being in algebra too, allows us to simplify it faster too. So it depends on whether we want to use combinatorics argument or an algebra argument to make our lives easier. Let's see. So you can see, this is the binomial theorem which I restated. So we want to count the number of elements in the power set. That's our first identity. I claim it's 2 to the power n. Well, how will you use a combinatorics argument first? You list out 1, 2, all the way to n, and then for the first one, to be in the power set means to be in one of the power set in the subsets. It means whether this element is or is not. So you have two choices. So every element has two choices to be in the subset or not in the subset. And so the total number of subsets will just be 2 to the power n. And this is the combinatorics argument for it. You might find this very easy, or you might not. And so let me present you the one that uses the algebraic expression of the binomial theorem. Consider the set of n elements over here. The power set cardinality is the total number of subsets of this S. And so that is the 0 element subset plus the 1 element subset plus all the way to the n element set. And hence a 0 element subset is just choosing 0 elements. A 1 element set is choosing 1 all the way to an n element set that chooses n. And so we can see this expression is just the addition of all the binomial coefficients, and from the binomial theorem we can deduce that x and y in this case must both be 1, and hence 1 plus 1 to the power n is the value of this expansion, and hence the power set has 2 to the power n elements. So you can see this is one use of the binomial theorem in a very basic identity, which is that the sum from r to 0 to n of n choose r equals 2 to the power n. Okay, let's move on to another basic identity. In this case, we want the alternating sum. Then obviously now x is still 1 but y is minus 1, and so the left hand side of the expression in the binomial theorem is 0, while the right hand side is the alternating sum. And so this clearly shows the alternating sum to be 0. Yes, you can create a combinatorics argument, but with the negative sign it makes it hard to choose to create a combinatorics argument. But with the binomial theorem, it can easily prove this identity. And there's one thing we can deduce from this, which is if we bring all the minus signs to the right hand side, which is basically all the n choose odd terms, which is here, it will equal to all the n choose even terms. And because the addition of these two is 2 to the power n, because it's all the binomial coefficients, which we already proved here, each of these must be 2 to the power n divided by 2, which gives us 2 to the power n minus 1. So n choose 0 plus all the way, all the even terms, is the same as n choose all the odd terms, which is 2 to the power n minus 1. And yes, again, you can use the combinatorics argument like earlier when we proved this power set, and we just have two choices here, but now you only need to choose the even terms. It is much faster to do it in this way. So these are just some basic identities, and there's much more identities you can prove using the binomial theorem, which will go on to our next video. So stick tuned and see you in our next video. I hope you have enjoyed this video and learned some interesting facts about the binomial theorem. Thank you.